Okay, so today's lesson, we're going to talk about recursion. So first we will talk about the definition of recursion. We'll have to talk about the call stack. We'll go step by step through two different examples. We'll talk briefly about recursion with arrays and strings, and then we'll talk just generally about tips for approaching recursion problems. These can be really tough, but they're also really fun, so let's get into it. So recursion, first off, let me move myself so I'm out of the way. There you go. So recursion occurs when a function calls itself. Recursion is an alternative to iteration where you would be using a loop. So what has always been helpful for me is knowing that whenever I'm using a loop, I can also refactor my code to make that recursive. So it ends up just being a choice as the developer. Times you're going to see recursion instead of iteration is when the recursive solution is easier to reason. Sometimes recursion can help us break up really big problems into smaller chunks. Sometimes recursive solutions are going to be easier to read than iterative solutions. And you'll see recursive solutions when it won't negatively affect the performance of your code, because recursion can be a memory hog. So again, these are all just considerations when you're deciding, should I use a loop, like a for loop, or should I use recursion on this problem? So before we talk about recursion, we have to talk about the call stack. JavaScript is what's called single-threaded, which means it can only run one function at a time. The call stack is the structure that JavaScript uses to figure out which function it should be running at any point in time. So too long didn't read, just know that JavaScript is not multitask. It runs one function at a time. That becomes very important. And so let's look at the call stack a little bit. I like to think of the call stack as like a stack of pancakes. That helps me visualize it. You can add a function 1, right? It gets added to the call stack. That's one pancake. Then function 2 gets added to the top of the call stack. That's another pancake. Function 3 gets added. That's another pancake. So all three of these functions in the call stack are waiting to be run. Now thinking about functions in the call stack as pancakes, which pancake will be eaten first? Yeah, the one on the top. No one's going to reach to the bottom of pancakes and pull out the one on the bottom and knock them all over. You're going to take the one off the top first, and then you have the second one is now on the top, and then the third one. And you're getting these return values one by one, starting with whatever is at the top of the call stack. And so let's look at an example of this. Again, whenever we call a function, it's added to the top of the call stack, and then JavaScript will execute whatever function is on top of the stack first. So let's say we have a function first. All it's doing is logging the string I am first, and we have a function second, which is logging the string I am second. We're going to invoke first, and then we'll invoke second. So when we invoke first, it gets added to the call stack, and then it's going to log up here in the top right corner. This is where I'll show our return values. It's going to log I am first. Then that gets off of the call stack because it has been completed. That function has run fully. Now we invoke second. That gets added to the top of the call stack. It console logs I am second, and it gets taken off because it was run fully. Wonderful. Now let's look at a slightly different example. Take a second just to notice what's different in this example. Yes, totally. So in our function first, we're console logging I am first, and then within that function, we're invoking the function second. And then after that, we're console logging first is finished. So when we invoke this new function first, let's see what's going to happen. We invoke first, it gets added to the call stack, it logs I am first. Then, since second is being invoked, that's now added to the top of the call stack. So we're going to run second before we finish running first. Because since that's now at the top of the call stack, JavaScript is going to run that one first. So we log I am second, because the function second ran. Then second gets taken off of the call stack, because it was run completely. Now we can go back to line 4 or line 5 and complete running the function first. So we log first is finished, first gets taken off of the call stack, and now we're completely done. So you can think of first as being paused while second ran, because that got added to the call stack on top of it. So we had to run that one first before we were able to finish running that first function. So our first kind of example that we're really going to step through today is this countdown example. It's just a function that counts down from some number to 1. So the way it's written now is with a beautiful for loop for let I equals num until or while I is greater than or equal to 1. We're going to decrement I, and we're just going to console log whatever I is. So when we call this with 5, we're seeing in our return values, we're logging 5, then 4, then 3, then 2, then 1. Then that's the end of our loop, and we're finished. Now we want to try to refactor this so we're not writing it in a loop anymore. One way of doing that is we could write this function countdown. It takes a num, and all we do is console log that number. We could manually run countdown of 5, countdown of 4, countdown of 3, and 2, and 1, and get the same return output. But we don't want to manually have to run all of that code, right? The code can kind of be doing it for us. And notice, how are the arguments changing between each of these calls? Yeah, they're just being decremented by 1 each time. So instead of us manually calling it over and over, let's have countdown call itself, but subtracting 1 from num each time. So now countdown takes num, console logs that num, and then it calls itself with num minus 1. So think for a second what this is going to look like on the call stack when we call this with countdown of 5. Okay, let's look at this. So we call countdown of 5, which will log 5. Then it calls countdown of 4, which logs 4, which then calls countdown of 3, which logs 3, which then calls countdown of 2, which logs 2, wonderful, which then calls countdown of 1, which logs 1. Okay, we did it, but now that calls countdown of 0 and logs 0, and then that calls countdown of -1 and logs -1, oh no, and so on and so forth. Oh no, what happened? So what happened is that we kept going and kept going and kept going until eventually we're going to get this fun, not fun error of your maximum call stack size has exceeded. So we effectively ran out of memory to continue to call that function because it just ran forever, right? We never told it to stop running at any point. It was wonderful that we were decrementing 1 each time, but we never told the function, okay, stop here. If you've ever used or heard of Stack Overflow, this is a really common and really wonderful website that a lot of developers use, actually probably all developers use. People just add code problems, code questions, and other people respond to them. The name and the logo here is a reference to having too much in the stack, right, and then it's overflowing. So we don't want that to happen. We want to be able to stop that while still recursively calling a function. So let's see if we can do what we were doing before, but write a stop condition so the function eventually stops calling itself. So in recursive functions, we call the stop condition a base case. That's pretty much whatever the input is that tells the function, okay, we want to stop running here. So when do you want that function to stop running? Right, in our case, it was when our num is less than 1, because we want it to be able to count down all the way to 1, and then if there's a number less than 1, like 0, being put in as an input, we want to just console log the string done, right? We want to hop out of that function and say we're done now. So if the number is less than 1, we will log done. Otherwise, we'll log that number and we'll call countdown of num minus 1, just like we did before. So let's see this with countdown of 3. We call countdown of 3, it logs 3, because if num is less than 1, it's not, else console log 3 and call countdown of 3 minus 1. So now we're logging 2, we're calling countdown of 1, we're logging 1, which is going to then call countdown of 1 minus 1, which is 0. So in this case, we're saying if num is less than 1, which it is because it's 0, we're console logging done, and then that's the end of countdown of 0. So that gets taken off the call stack. Remember, countdown of 1 was paused while we were running countdown of 0, but now that we've run countdown of 0, we can take countdown of 1 off the call stack, we can take countdown 2, countdown of 3 off of the call stack, and our function has worked properly. We got 3, 2, 1, and done. So 2 takeaways from that: we need to define a base case. We'll say this a bunch of times, we'll keep saying it because it's very easy to forget once you start getting in more complex problems. You need to know, tell your function when to stop running. And then 2, your recursive case must change the input to the function so that you'll eventually trigger that base case. So your recursive case wants to call itself and then change the input such that you're getting closer and closer to the base case until eventually you get there and you stop. So that was just console logging numbers. Recursion can be a bit more complicated when the function has to return a value. Good practice is always going to start by defining a base case, and then the base cases often occur when there's some sort of simple input that expects a simple output. So thinking about the sum of a single number is that number, right? If you're left with just one number left, the sum of that is itself. So that's a nice base case, an example like that. You want to always test that the base case works before working with the recursive case. So let's try an example now, a bit more complicated. We're defining a function called factorial, which takes a number and returns the factorial, or num, exclamation point, that's the syntax, of that number. So as a reminder, if you haven't done this in a long time, or if you've never done this, that's okay. 0 exclamation point, or any sort of num exclamation point, is how you say the factorial of that number. And the factorial is effectively the number times all of the numbers smaller than it until 1. So the factorial of 0 is equal to 1. That's just a thing you have to know. It just is what mathematicians have decided. And then 1 factorial is also 1. 2 factorial is 2 because it's 2 times 1. 3 factorial is 3 times 2 times 1, which equals 6. 4 factorial is 4 times 3 times 2 times 1, which equals 24. And 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 120. So you can do this with any number, but that's the pattern of factorial. So think for a second, what are the simple inputs and outputs we could use to build a base case here? Right? When would we want to tell our function to stop running? Okay, if you said when num equals 0 or 1, you were exactly correct. So again, if you look at these examples, once the input is either 1 or 0, we want to just return 1 as the factorial, and we want our function to stop running. So our base case is if num equals 0 or num equals 1, just return 1. And remember, you want to test that this works before you try your recursive case. So we're invoking this function right now with 0, we're invoking it with 1, we're seeing both of those return 1, we're not exceeding our maximum call stack. This looks good so far. So now we want to think about our recursive case. We need to remember that our recursive case has to bring our number closer and closer to 1 or 0 so that we eventually hit our base case. And notice this pattern, if you didn't already. The factorial of each number is just the number itself times the factorial of the number before it. So factorial of 2 is just 2 times the factorial of 1. The factorial of 3 is just 3 times the factorial of 2. The factorial of 4 is 4 times the factorial of 3, etc., etc. So you start to see this pattern, and you can imagine how we might use recursion to call this factorial function itself to get us closer and closer to our base case of 0 or 1. So again, we know we have to call factorial again in our recursive case, and we want to get that input closer to 1 or 0. So what we're going to do, which you maybe imagined already, is we're going to let our result be equal to the num times the factorial of num minus 1. Again, we notice this pattern. The factorial of any number is just that number itself times the factorial of the number minus 1. So that's going to be our recursive case here. Then we will return that result. Okay, so you always want to start testing your recursive case with the simplest possible input. So let's just try it with 2 right now. We'll let the factorial result be equal to the invocation of factorial with 2. And then we're going to log the factorial result so we can see what we're returning. In this case, we're showing you the call stack and also the return value as it changes so we can see things move step by step. So we call factorial of 2, which is going to go into our function at line 3. If the num is equal to 0 or 1, it's not. So we move out here to line 9. Let the result equal num, which is 2, times the factorial of 2 minus 1. So our return value is going to be 2 times the factorial of 1, which adds factorial of 1 to our call stack. Factorial of 1 is going to go into that first if statement. If num is equal to 1, it is. Return 1. So we have that return value. So now we can go back to complete factorial of 2, which is 2 times 1, which gives us 2. And we'll finally end up getting a return value of 2. So let's try that with 5 now so we can see a couple more steps. When we call factorial of 5, that goes into the second portion of our code block, into line 8, where we're calling 5 times factorial of 4, which then adds factorial of 4 to our call stack, which wants to return 4 times the factorial of 3, which adds factorial of 3 to our call stack. That's calling 3 times factorial of 2, which adds factorial of 2 to our call stack. 2 times factorial of 1 calls factorial 1. Now we get a return value of 1, so we can start unpausing each of those functions in our call stack. We get 2 times 1, which returns 2, which gives us 3 times 2, which returns 6. Keep going back down, 4 times 6 returns 24, and finally 5 times 24 returns our final value of 120. So again, we were adding pancakes to our stack until we got to our base case, and then we started taking them off from the top until we got all the way down to the bottom. So 3 takeaways from our factorial problem. 1, always write your base case first. Again, we'll say it a million times, always write it first, and then test it with simple inputs and outputs. When you've written your base case, you want to test your recursive case with the simplest possible input to make sure that that is working correctly. Then you can test your function with more complex inputs. Also, we won't talk about this lesson. We can get into this next lesson, but using Chrome's debugger can be really helpful to help you inspect your recursive calls, because console logs will not be as useful since we're kind of pausing certain functions and getting return values before unpausing others in the call stack. We're not going to be able to see that with console logs like we did in this example. But using Chrome's debugger, it will actually pause at each step and let you see what the value is at different steps. So again, we can get into how to use Chrome's debugger next lesson. Okay, so now let's look at this example in the debugger so we can confirm what's happening. So I'm using VS Code and I'm using the extension for Chrome's debugger. I'm just going to put a little stop here so we can watch what the num is as we go through, and we can watch our call stack here. So we can launch this, and then let's bring me back. So right now, we're calling factorial of 10 now. So you can see our num is 10, and factorial has been called once in the call stack. Now if we step through it, num is now 9, factorial has been called again. We've got 2 of those functions in the call stack. And we can continue to step through this, and you're seeing our num continue to decrement and our call stack building up and building up and building up until that num got to 1, and then everything cascaded and everything was able to be returned out of that call stack. So quickly, recursion and iterables, like arrays and strings, you can use recursion with any data type in JavaScript. If you're asked to recurse through an array or a string, the base case is often when the iterable is empty or has a length of 1. So imagine finding the sum of numbers in an array. That base case might be when your array only has one more number in it, because the sum of one number is just that number. So you can take an array and then keep shortening it until you get just one number left. So with that, if the base case required the iterable to have a length of 1 or 0, it must mean that your recursive call has to reduce the length of the iterable with every recursive call. So again, with that array, each time you call your function, you want to shorten that array until you end up just with a length of 1 or 0, and then that's what you're returning. Nested arrays can be approached a bit differently, but we will talk about that later in our next unit. And so we can't emphasize enough to start with your base case, test your recursive case with the simplest possible inputs, ask yourself, what type of thing should my function return? And your base case and your recursive case should return the same type of thing. That's also important to remember. Use console logs or the debugger. And if you get super stuck on a recursive problem, try writing it iteratively, so how you normally would with a loop. That can reveal the inner workings of the recursion and then help you see how you might turn that loop into a recursive solution. So recap, recursion is just when a function calls itself. The call stack is important because JavaScript is single-threaded, so it's only going to run one function at a time. The call stack allows it to decide what functions to run at what time. We went through 2 examples. Feel free to go back in the video to rewatch those, work through them on your own to see if you can figure that out. You'll see those examples a couple more times before you're done with your bootcamp experience. And when approaching recursion problems, think about, what do I need to output? What is my base case going to be? And then how can I make that input get closer and closer to my base case? Really great work. We'll come back to recursion and some more complex problems soon.